We'll begin our conversation about combinatorics and probability theory with a discussion of factorials. But first, what is combinatorics? Well, it's just a mathematical way of discussing the concept of counting. That is, how many of some combinations are possible, for example. How many different ways can I rearrange something? So counting seems easy. It's one of the first mathematical things you do as a human being. But it can become very delicate and quite, I would say, for lack of a better word, complicated. It's difficult to keep your head straight sometimes as you try to count these things. In order to be able to solve the problems we are interested in, we need a few notions. One of them is what's called the factorial, and then the related notion of binomial coefficient. So we'll start with a discussion of these mathematical tools. What is the factorial? Well, it's just a notation. What it says is if I take the factorial of some integer or some whole number, that value is equal to the product of that integer times the integer less than it, times the integer less than it, all the way down to 1. So in essence, it's simply the product of itself with all positive integers less than it. So as an example, 2 factorial is the product of 2 and all positive whole numbers or integers less than it. So 2 times 1, and then I stop. So this is equal to 2. 3 factorial is equal to 3 times the product of all integers less than it, times 2 times 1, so 6. 4 factorial is 4 times 3 times 2 times 1, so 24. In general, for any integer n, I can write n factorial as n times n minus 1 times n minus 2. And I repeat this process down to 2 times 1. An important note here is that by convention, 0 factorial is not 0 but 1. This is just to make certain formula in terms of factorials work out correctly. But when I say by convention, I mean it's not necessarily completely obvious that it should be equal to 1. But we set it to be that to get the kind of nice formulas to work out correctly. So I'll make a remark that it's helpful to actually write out this type of long multiplication when working with factorials. So to actually write things out like this, it lets us see patterns in the factorials more easily. And will also let us perform operations with them more easily, such as cancellations. So we can look at a few examples now. Right, just to summarize what I had already written, these are, I think, very good concepts to internalize. What is the formula for the factorial, and then also certain standard factorial values, namely 1 factorial, 2 factorial, 3 factorial, 4 factorial. And then we have this guy here. This is called the binomial coefficient. And it is read, how does one call this? This is read as n choose k. Why do we say it as n choose k? Well, it turns out that this number is related to the number of ways of choosing groups of size k from a collection of n different things. We'll make this more concrete when we discuss combinatorics in the future. But for now, it's important to know that this is called the binomial coefficient and what the formula for it is. So to compute n choose k, we take n factorial here and divide by k factorial and also divide by n minus k factorial. Let's look at some examples. So how would I compute 5 factorial? Well, I think one of the first things we could do is try to go to the formula. So what is 5 factorial? It's 5 times 4 times 3, 2, 1. So I write that out. and I try and simplify things. So this is 20, this is 6, so I get 120. So a nice early calculation. 6 factorial divided by 5 factorial. Now there's two ways I think to do this. There's the naive way in which you compute 6 factorial, then you compute 5 factorial, and then you divide those two numbers. The slicker way, which I encourage you to try to do, is to write out the rule for factorial and see that we'll get many cancellations in this division. So what is 6 factorial? It's 6 times 5 times 4 times 3 times 2 times 1. And I divide by 5 times 4 times 3 times 2 times 1. So all I've done is write out the formula for 6 factorial and 5 factorial. And now notice everything cancels almost. This 5 cancels with this 5. This 4 cancels with this 4. And I just get, well, I guess this cancels too. 6 divided by 1, so 6. Very slick, I think. Now, just to go back to the naive way, one could compute that 6 factorial is equal to 720, and 5 factorial we just saw was 120. So that 6 factorial over 5 factorial is 720 over 120, which one could show to be 6. So an equally valid way to do it. The reason I showed you my way first, or I shouldn't say it's my way, it's quite standard, is because it works in general. That this illustrates a general principle of factorials, which we will look at right now. So here I have a more abstract example. We're looking at n factorial divided by n minus 1 factorial. So for example, if I plug in n equals 100, this would be 100 factorial divided by 99 factorial. And now the method that we looked at second wouldn't really work so well, because computing 100 factorial is not easy, nor is computing 99 factorial. So trying to compute them separately and then divide is really quite a bad idea. What we should do instead is find a general mathematical principle here. And we can do that by expanding n factorial and n minus 1 factorial in the same way we did in the previous example. So we can write that this is n times, I'll put this off to the side, n minus 1 times n minus 2, and so on down to 2 times 1. And then n minus 1 factorial is n minus 1 times n minus 2 times 2 times 1. And as before, we'll get many cancellations. Let's look at what cancels. The 2's cancel, the n minus 2's, the n minus 1's. So I just get n on the top and 1 on the bottom. So just n. What does this mean for my sort of particular example of n equals 100? Well, even though I couldn't compute n factorial and n minus 1 factorial in this case, I could tell you that this is just equal to 100. So this is a nice way of understanding factorials. I don't always need to be able to compute all of them in order to compute certain quantities related to them. That is, it's easier to compute n factorial over n minus 1 factorial than it is to compute either separately. So here's just a quick example. This basically just tests, do you know what 0 factorial is? Tempting to say 0, but it's actually 1. Right? So this is 1 divided by 2, 1/2. Now we'll look at an example of this binomial coefficient. Right? So this is read as 6 choose 2. We'll make precise in what sense we mean this, but under certain assumptions, this number is equal to the number of ways of choosing groups of size 2 from a larger group of size 6. So you could imagine maybe having 6 people and you want to find all different possible pairings among them. This is related to that. So we'll follow the formula. N is equal to 6 here, and k is equal to 2. So I get n factorial divided by k factorial times n minus k factorial. So just plugging into the formula, I get this. And now we have 2 options. On the one hand, we could compute all the factorials individually and figure things out, or we could use these cancellation tricks, which I'm going to do. I'm going to say this is equal to 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 4. 3, 2, 1. And since everything's being multiplied together, everything has potential to be canceled. So what I'll do now is I'll look for things on the bottom that I can cancel with things on the top. The 4's cancel, 3's, 2's, 1. And I'm left with 6 times 5 divided by 2 times 1. So 30 divided by 15. 30 divided by 2. So 15. Think about this as a way of computing compared to finding 6 factorial, finding 2 factorial, finding 4 factorial, and putting them all together. In this case, that would be what? I think 720 divided by 48. Did you know that that was 15? I didn't. Okay. Here's a quick example. 3 choose 3. So the question is, how many ways are there to choose 3 elements from a group of 3? Well, I think intuitively it should just be 1. You have to pick them all. If I have 3 people and I want to know how many trios can I form out of them, well, it's just 1. It's the trio formed from taking all of them. Let's see if it works from the formula. So here, n equals 3, k equals 3. So this is equal to 3 factorial over 3 factorial times 3 minus 3 factorial. Okay, and this is an important moment to remember what 0 factorial is. It's not 0, it's 1. And we should be thankful for that. Otherwise, our formula wouldn't work here because we would wind up dividing by 0, which is not allowed. Okay, so this is 3 factorial over 3 factorial times 1. So 3 factorial over 3 factorial. So I just end up with 1. So great. My intuition for how choosing groups work, or should work, fits with this definition. Okay, now we'll move on to making these notions of counting more precise. That is, we will actually explicitly relate the binomial coefficient and factorials to specific problems in combinatorics. But before we do that, we'll look at one last example that, again, kind of looks strange, but it's more about testing definitions than anything else. This is 7 choose 2, or rather 7 choose 0. So one would ask, how many ways are there to choose 0 things from 7 elements? Well, only 1. The way I choose this is by choosing nothing. That's one possibility. Does it fit the definition? Well, I have 7 factorial divided by 0 factorial times 7 minus 0 factorial. So just simplifying everything out. And I end up in a similar situation where I end up with some number factorial divided by that same number factorial. So just 1. So again, this doesn't really do too much conceptually, but it is important to understand the definition. So we have one more here. So we would read this as 5 choose 3. Okay, so how many ways can I choose groups of 3 from a set of 5 elements is what we will establish shortly. So 5 factorial divided by 3 factorial times 5 minus 3 factorial. Right, so let's play the same game where I cancel factors where I can. So 5 times 3 times 2 times 1, times 4. 3 times 2 times 1 times 2 times 1. So what cancels? 2. So I just end up with 5 times 4 divided by 2 times 1. So 20 divided by 2. So just 10. So we've seen many different examples of how to compute factorials alone and also binomial coefficients, which of course require factorials. So now let's get into actually relating these to problems in combinatorics.